Today, we're going to decode something called DSA. That's data structures and algorithms. Sounds a bit techy, right? But trust me, it's the secret engine that makes your entire digital world, will work. And we're about to pop the hood. So, let's kick things off with a question. Have you ever wondered how an app can search through a million items and find the one thing you want in a split second? It feels like magic, doesn't it? But it's not. And it's not just about having a super fast computer either. It's all about thinking smarter. And that brings us right here, to the heart of the problem. We'll call it the billion-item search. This is the kind of massive challenge that forces programmers to get really, really creative. You see, as our apps get more and more complex, filled with tons of data, you can't just throw a faster computer at the problem and hope for the best. It just doesn't work. Once you hit a million or a billion records, things start to get really sluggish. And when you have thousands of people trying to use the app all at once, the whole thing can just grind to a halt. So if a faster machine isn't the answer, then what is? Well, this is where developers reach into their special toolkit. And that toolkit is called data structures and algorithms. Okay, first up, data structures. The easiest way to think about these, they're like blueprints for organizing your information. I mean, you wouldn't just dump all your tools in a giant messy pile in the garage, right? No, you'd get a toolbox with little compartments and drawers. That's exactly what a data structure does for data. It gives it shape, it gives it order. And if the data structure is your perfectly organized toolbox, then algorithms, well, they're the instruction manual, the step-by-step recipe that tells you exactly how to use those tools to get a job done. It's a super precise, no-nonsense set of rules for the computer to follow to solve a specific problem. And let me tell you, this toolkit is packed. For organizing your data, you've got things like arrays, linked lists, all the way up to more complex stuff like trees and graphs. And for working with that data, you have all sorts of algorithms for searching, sorting, you name it. The real skill, the art of it all, is knowing which tool to pick for which job. Okay, but with all those choices, how in the world do you know which one is the best one? The answer is fascinating. It's not about raw speed. It's about being smart. It's about working smarter, not just faster. So how do we actually measure smarter? Well, you can't just time an algorithm with a stopwatch on your computer. That's totally unreliable. Your results would change depending on the machine. Instead, programmers use this really cool idea called asymptotic analysis. Basically, you don't care how fast it is for a small amount of data. You care about how its performance changes as the data gets bigger and bigger and bigger. It's all about the order of growth. And to really see why this matters, let's set up the ultimate showdown. We're going to take a simple, kind of dumb algorithm, we'll call it a linear search, and run it on a supercomputer, and we'll pit it against a much, much smarter algorithm, a binary search, running on a clunky old laptop. Who do you think wins? Okay, check this out. The results are, honestly, they're mind-blowing. With just 10 little items. Yeah, the supercomputer wins, no surprise. But watch what happens when we add more data. At a million items, the slow laptop with the smart algorithm is already 10 times faster. But the real shocker, at 1 billion items, the smart algorithm on the slow PC finishes in about 8 hours. The supercomputer, it would take over 6 years. This just proves it. A better algorithm doesn't just beat a faster machine, it absolutely demolishes it. And that leads us to this huge, crucial takeaway. Basically, it means that once you're dealing with enough data, the speed of your computer almost doesn't matter anymore. The intelligence of your algorithm is everything. A smarter approach will always win. Period. And look, this isn't just some abstract theoretical stuff for computer science classes. No way. DSA is the invisible engine that powers the world you use every single day. Think about Google search. Every single time you type something into that search bar, you're kicking off one of the most complex DSA systems on the planet. It's using unbelievably efficient data structures and crazy powerful algorithms to sift through trillions of web pages and find the exact one you need. In, what, less than a second? It's incredible. Or what about when you're scrolling through social media? You're actually interacting with a giant graph. Every person is a dot, and every connection or friendship is a line between the dots. And it's these powerful algorithms that crawl through that massive web to suggest new friends or decide what shows up in your feed. And hey, ever used Google Maps or Waze to get home? That's DSA in action, right there on your phone. The app sees the entire road network as a massive graph and runs a shortest path algorithm to find you the quickest route, even factoring in all the crazy rush hour traffic. It's solving a super complex problem in real time. Okay, so we've seen how DSA is the secret sauce behind our apps, but why does this really matter to you? Because learning this stuff isn't just for coders. It's about learning a whole new way to think. I mean, if you're in tech or want to be, knowing DSA is, frankly, non-negotiable. It's what Google, Meta, and all the big companies test you on in their interviews. It lets you write code that's not just functional, but fast and scalable. But even beyond that, it really does give you a powerful mental toolkit for breaking down any big, messy problem you face. So when you boil it all down, DSA is so much more than just a computer science topic. It's like a universal language for problem solving. It teaches us to look at the world's biggest, most intimidating challenges not as impossible roadblocks, but just as complex puzzles. Puzzles that are waiting for a really elegant, smart solution. And that leaves us with one final thought. What algorithm will you design?